Hello YouTube! It's undeniable that nature is beauty. And we physicists have the job to describe this beauty and to talk about this beauty and to think what makes this beauty so beautiful. But to speak with each another, we need some form of language to talk with. If I talk to another German guy in German, that's fine. If I talk to you, I have to talk English, because that's the common language we share. And physicists has also a common language they share, which is the so-called SI units from the French Système International des Units, in which we find the basic ways to describe the universe. Let's start with the meter. We all know the meter. We all use the meter, or maybe we don't. It is probably the most important SI unit, the most important mechanical, of course, and it describes a measurement of length, or distance, or height, or width. All the same words for what is the length. And we describe this length with the so-called meter. What does it mean that we describe it with the meter? Well, every measurement we take on a length, we say, oh, this compares to a meter in that and that way. For example, it's 5 times a meter, then we have 5 meters. And of course, we can use other units like foot, or feet in the plural, or miles, or inches. But when we want to use the physical, the Système International, then we have to use the meter. We can say, oh, something is 3 meters long, and that translates into some unit of inches or mile. The question is though, how was a meter defined? At first we had a standard meter, and that was pretty awesome. We had one huge stick which was like 1 meter long, and we carried it all along the way, and we said, oh, let's lay it down here another time, and oh, that's about 2 meters. But that was not very exact. So we took another measurement, and that was a little bit more exact. There's one fixed constant in the universe, beneath others, which is the speed of light. And when we define a second and the speed of light, the meter is what we get. The meter is defined in modern ways as the distance light travels in 1 over 299,729,458 seconds. In 1/3 times 10 to the power of -8 of a second, light travels already a whole meter. In this really small time, light has traveled a whole meter. Don't think though a meter was small. A meter is about 3.28 feet, which is quite okay. Well, the definition uses the second, and the second is the next unit we want to talk about, the unit of time. And back in the day it was defined as 1 over 68,400th of a solar day in the year 1900, a particular summer solar day. And since then the definition has changed slightly, and this one is a bit more difficult and a bit more impractical for daily use. So I use this one as daily use, and this one is like the formal definition. By the way, this number is nothing crazy. It's like 60 for 60 seconds in a minute, times 60 for 60 minutes in an hour, times 24 for 24 hours in a day. So it's really just the seconds in a day, so the seconds of a solar day in 1900. They use the solar day here, by the way, because the solar day is more exact. If you use the normal day, it's like 4 seconds or something shorter. So then we have to use leap years and that stuff, and that's a bit nonsensical for formal definitions. Okay, the next one. This one is the formal definition of the second, and it's a bit complicated. It's 9,129,631,770 times the period of the electromagnetic radiation caused by electrons switching the hyperfine structure of cesium-133. So what do I mean by that? That's quite a difficult definition. Well, it's actually pretty simple. So we have an atom of cesium-133. It's just one atom, one special atom. And around these atoms, sometimes electrons fly. And these electrons round and go round and go round. But they can go round on different distances from the core, from the nucleus. And those distances usually correlate with some sort of energy. So when a electron goes from a further distance to a closer distance, that's a certain energy that is released. And usually that energy is released as electromagnetic radiation, like the light that we see. In this case it's not really light, but it's electromagnetic radiation. And this electromagnetic radiation has a special period that we can measure. And if we take a special number times that period, we get a second, because this period is 1 over this times a second. Okay, let's get ahead to the next unit. That's the unit of mass, and not mass, and that's the kilogram, or kilogram, as I should say. Sorry for my German accent. That's 1 kilogram, and we have only defined it as a standard kilogram in Paris. Maybe the Higgs boson will change some of that, but right now we only have the standard kilogram in Paris in some cellar, and it's under its thick vacuum bell, so that none of the weight gets deleted by rust or something similar. But we also have taken a weight of platinum iridium, which serves the purpose of preserving the weight. So whenever we measure something in kilograms or grams or whatever, we usually take out this ancient kilogram, this standard kilogram in Paris, and then we compare them to. Of course, we have a couple of sister kilograms, which we usually use and only compare those with the standard kilogram. But directly or indirectly, in the end, everything is compared to this 1 kilogram in Paris. Let's skip ahead to the next one. The electric current has a special one, which is the Ampere, from the French physicist Ampere, or however you pronounce them. And this one is really crazy. It's the strength of the electric current required to generate 2 times 10 to the negative 7 newtons between two infinite conductors that are 1 meter apart. So the conductors are infinitely long to just straight lines, infinitely long. They're 1 meter apart, and only because there's just some current running through, there's generating a force between them two, and we can measure that force. And if that force is 2 to the 10 and to the negative 7, then we have 1 ampere running through these currents. Interestingly, this definition uses other definitions. If we take, for example, the meter right here and the Newton, we see that we use all 3 mechanical units. The Newton is nothing else but a kilogram, kilogram times meter divided through a second squared. So we have seconds, meters and kilograms, which all come together to define the ampere. Now, the next unit is also very interesting. It's from thermodynamics, and it's the temperature. We measure it in Kelvin. That's what we measure it in, and usually not Fahrenheit. Fahrenheit is more informal and non-physical, but in physics we measure it with Kelvin. Kelvin is defined as 1 over 237.16 of the thermodynamic temperature of H2O in its triple point. That's one special point that's only 0.01 degrees above 0 degrees Celsius. So what is Celsius? Celsius is another unit of measuring the temperature. Celsius is 1/100th of the temperature of H2O to boil minus the temperature of H2O to melt. And that was the usual definition we used. But as we discovered that pressure indicates when a substance is going to boil or melt, then we had to change it. Because under certain pressures, water boiled much earlier or much later. So this wasn't really good anymore. Still, sometimes we still use the Celsius in some rare cases, and a Celsius is just a Kelvin, or let's say 0 Celsius. 0 Celsius is just the Kelvin plus 237.15. It's quite interesting, it's 15, not 16 here. If you want to get from Celsius to Kelvin, you can just add this 237.15, and if you want to get from Kelvin to Celsius, you can just subtract this number. One of the certainly weirder definitions is the chemical amount of substance. In German we call it the Stoffmenge, and it's called with a symbol N, and it's 1 mole. And 1 mole is the number of atoms of C12 in 12 grams of C12, and that's about the Avogadro's number, which is 6.022 and some other digits times 10 to the power of 23. That's actually quite a lot, but it's quite strange that we have this definition, because we count usually 1, 2, 3, 4, 5, 6, so counting is not really a measurement. We do not compare it to anything. You can say, oh, we have 3 things here. That doesn't mean that we have a comparison to something else. Usually we can just say it's 3 times more than what we have. That's a comparison. But just 3 things, that's not really comparing to anything. So to have just a number, the amount of substance in here, is quite interesting. Yet the champions use this amount of substance so often that it should remain a SI unit. Lastly, we have like the weirdest of them all, which I included under other, or you could include it under optics, and that is the luminosity, IV, and its candela is a unit that we take, or CD shortened, and it's quite interestingly defined. It's a light with frequency of 540 to the times 10 to the 12th power hertz, and this light has to have a certain strength, and that is a power of 1 over 683 watts of radiation per steradian. And what's a steradian? Well, it's a measurement of an angle, but not really an angle in one dimension, like this one here, but a measurement of an angle in 2 dimensions. So it's a area angle, you could say. These are all the units, the SI units, we physicists use to talk about things. Yet they are not all units we use, or even everything we use, because we have certain things that we do with these units. For example, we calculate a velocity, and then we have meters per second. We have an acceleration, we have meters per second squared, and so on. So we have units that we derive from these SI units. And furthermore, we have something else. We can add some syllables to our meter or to our second and change them. We can, for example, say we have a kilometer. The kilometer is nothing else but saying that we have thousands meter. And if we use a decimeter, we have hundreds of a tenth of the meter. If you use a centimeter, we have a hundredth of a meter. If you use a millimeter, we have a thousandth of a millimeter, of a meter. Sorry. And we can use these syllables to expand our ideas of these SI units. So in the next video, we are going to look at these syllables we can put in front of our SI units to expand them for greater use. For example, we can't always say some distances in meters because it gets quite chaotic. The numbers get quite high. For example, the light speed in meters is in meters per second is 299,792,458 meters per second. And that number is quite high. And if we shorten it, we can use kilometers, for example, to get around 300,000 kilometers per second. And that's much shorter and much easier to say. The same goes for grams, tons, hours, minutes, and so on. You can expand that list quite far, and we are going to look at that the next time. I hope you enjoyed this session, and I hope we are going to see each other next time. And I excuse myself for my German accent and my terrible misspeakings. Okay, good luck. Until next time.